Hello, everyone. Today I'm going to talk about the HSAB principle, which is hard acid and bases principle. And this is like one of my favorite topics in chemistry. Before we actually get into it, I did just want to mention shortly that I designed this hoodie myself. And it literally says tunnel through or transition across like a quantum choice. And it has like a tunnel underneath the words. So if you are interested in this kind of chemistry nerd kind of clothes and hoodies and merchandise, it will be available on a website that I will share shortly on my YouTube channel. Okay, let's talk about what a hard acid or a hard base is. Okay, so a hard acid is characterized by, or even a base as well. A hard acid or a base, I'm just going to say acid or a base, is characterized by an atom, or it can be ion, or it can be a compound, by a high charge compound. And it's also a small sized compound or an atom. It's small in size. It has a high charge. Okay. And it's not easily polarized. That is for acids or metals, and polarizable for bases or nonmetals. So what I'm essentially saying here is that if you see an atom or a compound, it can be ionic or neutral, if that has a high charge on it, right, and has a smaller size. So if you will see compounds, for example, hydrogen, lithium, beryllium, magnesium with a high charge, +2, calcium, high charge, +2. All of these are really smaller size, right? Lithium and beryllium is a smaller size, but whenever you have magnesium and calcium with +2 charge on them, meaning that you will see a high charge on them, that would also be considered a smaller size, because high charges on metals, they would actually reduce the size of that metal, right? Because if you have a high charge, then it would reduce the overall size. That would make the metal not easily polarized. So what does that actually mean? It means that if you have H plus, right, Li plus, beryllium plus, beryllium 2 plus, magnesium 2 plus, calcium 2 plus, all of these metals, they're hard to polarize because their size is so small that another atom cannot actually come in, and it cannot really polarize it, or it cannot really influence it. Okay, that's the simplest explanation, which essentially means that you cannot really ask beryllium to easily be influenced by other atoms in the presence of other atoms. So all of these, it just because they're so small in size, right? Beryllium, magnesium, calcium and magnesium, because of the high charge, they become like smaller in size, right? Because they're smaller in size, they have a very strong personality. If we compare them, or if we make an analogy to human beings, they would have like really strong personality, strong opinions. They're very small. They're not ready to listen to other people. They're not ready to change their opinions, their minds. They're very, very opinionated. And that's why they're kind of like shut down. And because they're so shut down, they don't listen to other people. They're not influenced by other people. And that's why they're really short, smaller, right? So if you see atoms with the smaller, and if they're slightly bigger, like magnesium and calcium, but they have a high charge on them, that would be considered a part of a smaller personality. So if they have then smaller personality, then they are hard acids. So, well, again, clearly, if you have plus charge on them, we would consider them acids. They will be categorized under the category of acids. And for bases, if you'll see nonmetals and with the negative charges, they would be considered bases, right? So here, right over here, these are the examples of hard acids. And with the same logic, right, let's think about what would be the example of a hard base. So another point to keep in mind when we're thinking about a hard base is we want to think about electronegativity. So for bases, you also want to think about, they have, okay, we're talking about hard bases. They have high electronegativity as well. And their high electronegativity will make them hard to polarize or hard to be polarized again by other atoms or in the presence of other atoms, because the definition of electronegativity is they like to keep the electrons closer towards themselves, right? So if they're keeping electrons closer to themselves, they're not sharing it with the world, it's hard to make them share their electrons, right? Again, they have a very strong personality, they keep to themselves, they're not easily influenced, so they are part of a smaller circle. Again, they're part of smaller size and hard to polarize, and then you will see that they have a high electronegativity in terms of bases. Okay, so let's think about the examples of hard bases. So OH minus, right? Oxygen, very electronegative. So oxygen electronegative and hard to polarize. Okay. And oxygen electronegative and also has a small size. Think about oxygen, it lies here in the first row of the periodic table. That's the smallest size of the periodic table. If you go down the column, the size increases, right? And across the row, size decreases. So oxygen has a really small size as well, and then high electronegativity, and that's why OH minus is a part of a hard base. Okay, and then let's think about how about H2O? Again, oxygen is electronegative and has a smaller size. Again, also a hard base. How about O2 minus? Again, also has a high charge and small size and high electronegativity. So for bases, we'll usually look at electronegativity and we'll look at small size. Okay, so what can be the other examples of hard bases? So think about F minus, right? Fluorine, again, electronegative, is very small in size, right? How about chlorine minus, Cl minus, also electronegative, is smaller in size, as it's not as big as the bromine and iodine, but still kind of considered still smaller. So we'll still take that. We'll take that a part of a hard base. But if you want to think about sulfur now, right, because we are at the second row of the periodic table, and then you would say, oh, how about sulfur? Are any bases that are made of sulfur, would you consider them as hard bases? That's incorrect, because sulfur would now be considered not as electronegative as chlorine, right? Chlorine and this entire row in the periodic table is the highest electronegativity elements, and that's why these elements are the chlorine is also part of high electronegativity, and that's why it's under a hard base. But when we will think about sulfur compounds, now it will be considered a bigger atom, and that's why bigger atoms are now going to be categorized under soft acid and soft bases. Okay, all right, and now let's think about why are we thinking about hard acids and hard bases? Why are we categorizing them into two categories? It's because a lot of these observations have been made by scientists, where they saw that a lot of these hard acids only react with hard bases. And a lot of these soft acids react with soft bases, and then they came up with this theory that, okay, these we can see certain characteristics of these acids and these bases, and that's why from there they learned, oh, these acids actually have these smaller size and high charge in them, which is making them a hard acid. Okay, all right, so now let's look at soft acid and soft bases. So now, contrary to what we saw before, a soft acid is something which is easy to polarize, right? A soft acid would be easy to polarize. And as a result, it will have a higher or we could say bigger size, lower charge, bigger size, and a lower charge, because we know the result of having a high charge. The result is that usually whenever you see a high charge, I'm just gonna write that better really quick. Whenever we see a high charge, the size reduces because of the effective atomic number, or the effective nuclear charge on the atom decreases, so the size decreases. The effective nuclear charge increases, so the size decreases, right? But if you have a lower charge, right, the size doesn't really affect the size that much. So, and softer acids are characterized by bigger size. And again, we can think of this as human beings, right? Bigger personalities. If you are a bigger human being, right, you want to consider other people's opinions. You would be considerate of other people, of what they're saying, and that would make you a softer human being. So you're not going to be that hard of a human being, right? So you would be a softer human being. So that's like a nice way to kind of learn the definition of soft acid. So what are the examples of soft acid in terms of metals? Because whenever we're thinking about acids, we would think about metals and transition metals. So what are the examples of soft acids? So again, characterized by very low charge. So copper 1+, right? And then mercury +2. So you will usually see charges like +1 and +2. If you see +1 and +2, if you see them in a category of transition metals, choose them as softer acids, because transition metals are usually bigger in size. And then if you have +1, +2, categorize them as soft acid. But if you have +3, they would be considered a hard acid. And to give you an example, iridium +3, again, a transition metal over here, right? Iridium is right over here. Whenever we have iridium +3, because such a high charge, it would always be considered a hard acid. And also again, rhodium +3, right above. Cobalt +3, right above. They will all be considered as hard acid just because of the high charge, right? Whenever we see the charge is not so big, in the category of +1, +2, they would be considered softer acids. So Hg +2, cadmium +2, zinc +2, they're all transition metals. Transition metals are usually bigger in size, and because of a lot of these d orbitals that they have. And then +2 size, it's not a very high charge, so still a reasonable charge, so still in the category of soft acids. Okay, how about soft bases? Okay, so soft bases would still have, again, there would always be easy to polarize. You know, they're very amenable people. They're really good people in the society, so they're ready to be not really influenced. I wouldn't call it influence, but they would be considerate of other people. So they're very considerate of other people's opinions, and they want to involve other people. So they're bigger, they have bigger personalities. So you will see them having bigger sizes. So you would say they're big sized, right? So you can think of them as large atoms, and they would have lower electronegativity. Electron and my negative sign, this is literally a negative, really. Okay, so because they have lower electronegativity, they don't have a tendency to keep everything towards themselves, and because they're not keeping everything towards themselves, they're ready to share their electrons. Okay, and that's why they're softer. So whenever we're thinking about bases or non-metals, again, you want to think about atoms that are bigger in size. Again, like we saw sulfur, right? It is a non-metal. It's not too small. It is bigger in size. It's not very electronegative. That's why it will fall in this category. So all of these compounds, or R2S, meaning any compound of sulfur, would be considered a soft base. And then what else? I minus, okay, that's important. I minus iodine, okay, now it is it's still in the series of electronegative halogens, right? Fluorine, chlorine, bromine, iodine, but iodine is like really big. Now it has surpassed the size limit, and that's why now it's in the soft base category. Okay, and now if you want to think about Br minus, we'll talk about it in a sec right now, but let's finish soft bases first. Okay, the last thing that I do want to mention here is H minus, which is really important, I think. So now again, H minus is not that big in size, but it's very low electronegativity, right? And that's why it's considered as a soft base. And it's kind of confusing because when we saw H plus, it was in the category of a hard acid. But H minus, it's important to remember, is in the category of H minus is in the category of soft bases. Cool. Okay. Now let's talk about borderline acids and bases. So what is a borderline acid and a base? Whoopsies. So a borderline acid would be an acid which sometimes behaves as a soft acid, sometimes behaves as a weak or a hard acid, depending on the environment, right? Sometimes if you reacted with a weak base, with a softer base, sometimes it will react with a softer base, and sometimes it also reacts with a hard base. So that's why they're called borderline. So they're like chameleons. They sometimes go in that category, sometimes they go in that category. So what are the examples of borderline bases? Again, most of these metals which are really big in size, platinum +2, lead +2, what else? Iron +2, cobalt +2, right? So they still have high charge, they still are big in size. So sometimes they behave as hard acids, sometimes they'll behave as weak acids. So they're like in both the categories, they have their feet in both the ships. And same with the borderline bases. And an important thing to remember with the borderline bases is most of the nitrogen compounds that you will see like aniline would be nitrogen. They're mostly nitrogen compounds. They're usually like floating between acids and bases, or not acids and bases, between hard and soft. So aniline, pyridine, I would say RNH2. and Br minus, which is important again, because right over here, right, Br minus is big, and it's electronegative, but sometimes it goes in the category of soft base, sometimes hard base. But fluorine and chlorine, the one above that, is clearly differentiated by bromine. That fluorine and chlorine, which are above that, they're always soft, they're always hard bases. But the one after bromine, which is iodine, is big enough, crosses that category, and now that's why that is a softer base, right? So Br minus is like the differentiating one, which sometimes goes to the softer one, sometimes to the harder one. Okay, and then with this explanation, we have come to the end of this video, and I will see you guys next time. Have a great rest of your day.